Okay. Can everyone in the back hear me? Cool. Okay. So welcome to active TLS fingerprinting to identify C2 servers. We call our process JARM, and it's a tool by John Althouse, Andrew Smart, RJ Nunnally, and Mike Brady. So I'm RJ Nunnally, and a little bit about myself. I've been in the computing all my life, and I started out just repeatedly breaking a 286 my parents gave me. I'm probably the world's youngest COBOL developer, and I joined Salesforce 6 months ago as a security engineer.
I'm John Althouse. I drew a little picture of myself. That's me. I run threat detection at Salesforce.
All right, so first a little background on TLS fingerprinting. Back in 2017, JA3 was created by John Althouse, Jeff Atkinson, and Josh Atkins. It looks at the client hello message and creates a hash from the SSL version, accepted ciphers, list of extensions, elliptic curves, and elliptic curve formats. JA3S extends that functionality by also looking at the server hello message, and it further hashes the TLS version, cipher, and extensions. But that only gives you a peek into the TLS configuration. Because JA3 and JA3S are passive, the full extent of what the server supports cannot be determined, and an active approach is necessary, and that's where JARM comes in. So active fingerprinting is necessary because when an SSL or TLS session is initiated, the client starts with a hello message, and that contains all the ciphers, the SSL or TLS versions supported, and the extensions. The client then allows the server to choose which TLS version, cipher suites, and extensions will be used. The server sends that response back in a server hello message. So this is where JARM comes in. We hypothesized that server TLS implementations will have many variations, from the supported SSL or TLS versions to the supported and preferred cipher suites. That support can indicate a push for compatibility, security, or may reveal an out-of-date server. It also becomes fairly unique depending on the specific TLS stack that is implemented. JARM specifically is a fast TLS fingerprinting process. And the way it works is by sending the ciphers in different orders and a different list of ciphers and checking the response back from the server and doing this over and over again, we're able to develop a unique fingerprint. So you can see here, what we'll do is we'll send it first, like the ciphers in like the order of A, B, C, D, and then we'll reverse it. We'll send them back in like D, C, B, A. And then eventually we'll send different ciphers, and we'll do it over and over, and we'll fingerprint that. So to build this proof of concept out, we started with a modified version of the enum cipher script that's provided with Nmap. And just to be clear, this was just to make it a fast development process. It's not something that's necessary. That script was written in Lua, and it's very similar to what's available on SSL Labs provided by Qualys. One of the things that was very important for us is that we wanted to be able to scan the internet. And to do that, it has to be fast. So the enum script is very slow. It probably takes about 30 seconds per IP. Our process takes less than a second. And it turns out that it's pretty accurate. So this is our short fingerprint theory. And this just goes back into the process of sending those ciphers. So we send them normally, then we flip it, then we'll send the top half in reverse order, then we'll send the bottom half, and then we go from like the middle out. And we just record the responses, and those variations make up that unique fingerprint, and it's about 30 times faster than doing it the traditional method.
Just to reiterate here, so the idea here is that the servers will respond to different TLS packets based on the operating system that it's on, the version of the operating system, the packages that were used when creating the application, the versions of those packages, maybe even the order in which the packages are used. All of these different variables will cause the server to respond to TLS packets in a different way. with different ciphers, maybe choosing which cipher it chooses, which extensions it's going to accept. The order of those extensions, all of those things can vary based on all of the different little details that are used when building the application. So that's the whole idea behind this fingerprinting process. And so we're sending we're trying to send as few client hello packets to the servers as possible. So that it can be really fast, so that you can potentially scan the internet with this. So we want to just send as little as possible in order to get a unique fingerprint back, so that we can fingerprint the server, and then potentially use it for scanning the internet at speed.
Yes. Oh, I can just. Oh, is that even on?
No, here.
Okay, I'll use this. Okay. So this is just a slide real quick showing the 5 client hello packets for a specific TLS version, and that's all it is. So here's a real look into how we're building our hash. So this is just a modified output from the SSL enum cipher script, and it still has the scoring in it, but we removed it because it's not relevant to our purposes. So we have this output that comes out, which is the 5 responses, plus all the different SSL versions and TLS versions from the script. Then we concatenate all that together, and then we just hash that with MD5. And that's our JARM hash. So on to the preliminary results and what we found. So we fingerprinted the Alexa top 500 repeatedly, and then we also fingerprinted the top 1 million. What we found was consistency between various vendors or hosting platforms, and we also found that in the top 500, when we did it repeatedly, we got the same hashes back, indicating it's a fairly reliable hash. And here we go. So these are some real JARM hashes on the left, and the domains they resolve to on the right. So you can see that like Facebook, Instagram, Messenger, and WhatsApp.com all have the same JARM hash. You can also see that like Bing.com, Live.com, and Office.com all have the same hash. So it actually works pretty well.
That's it. Can you do this one too? Test. There we go. Cool. With this, if you were to scan the whole internet, you could potentially easily identify if a server belongs to Google or if it belongs to Facebook, no matter what the domain is for that server, or what the certificate details are, if it's using like a Let's Encrypt generic certificate or something like that. But with the JARM hash, you could potentially be able to identify, well, this one actually belongs to Google, if it's using the same application that all the other Google servers are using for TLS, handling TLS.
So after that, what we did is we found some known malware out there. So this is Trickbot, and we found 4 different unique hashes for Trickbot. When we cross-referenced that against the Alexa top 1 million, we didn't get a single hit. So
yeah, this slide really kind of like undersells it, but potentially, if you were to scan the internet or use like some service that scans the internet, I'm sure Andrew Morris can tell you all about them. Then you could potentially find all of the Trickbot C2 servers or some malware C2 on the internet, even if they're not being utilized yet. So, like set up, but have not been actually deployed to the malware. So traditionally, we find out about these Trickbot servers, or whatever C2 server. We find out about them by running samples of the malware and then seeing what they communicate to. Well, with this, you potentially don't even need the samples anymore. You could just scan the whole internet and find them potentially. We still need to do a bit of research here, but the potential is really exciting. And another thing to note about Trickbot is that the Trickbot Stage 1 is generally like some compromised proxy router or something that's gonna pass the traffic through. So what we're actually fingerprinting here is the stage, or the stage 2 of Trickbot. So we're fingerprinting the TLS server. So the packet is actually being passed through the IP address to the actual Trickbot like stage 2 command and control server, and we're fingerprinting the TLS application on the C2 server, not the actual IP address for Trickbot, because those are just proxies that send the traffic through. So really interesting. And from all the ones from Abuse.ch, they just pretty even spread across these 4 fingerprints. And like RJ said, no overlap with the Alexa Top 1 Million. Completely unique. Now, we haven't scanned the whole internet yet, but preliminary results are very promising.
And continuing that note, we also expanded this out to look for Tor nodes.
Yeah, so we just needed more examples. So Tor nodes tend to have those top 4 tend to be what we see from Tor exit nodes, but also just across all Tor nodes, so Tor nodes that you would be connecting into. But if you hit the next slide, RJ, what's interesting here is that there are one-offs, and not a lot of one-offs, just a couple one-offs on these all the Tor nodes on the internet, which means that Tor application potentially has been changed a little bit. Maybe they're doing something slightly different with the Tor traffic. You don't know. It's interesting.
So this segues nicely into the next use case, which is for compliance and patching. So by checking the drone fingerprints of, say, all the servers in your infrastructure, we're easily able to determine if one of those servers isn't like the other. So then that would indicate that it's probably out of compliance and needs patching. So here you can see there are 72 total servers, 71 are all the same, one slightly different, and we can narrow in on it very easily.
So what happened, I guess, when we scanned the Tor infrastructure is we accidentally did a compliance check on Tor and found a couple anomalies. So it's interesting.
So yeah, the impact of all this is pretty interesting because we can potentially proactively block C2 servers based on their drone fingerprints. The biggest problem with that, of course, is we need to make sure that we don't have any false positives, or else you're potentially blocking legitimate traffic. And it could make for very easy compliance checks as well. Oops. So what's next? We still need to clean up the code base. So we're going to rewrite the code from scratch and not rely on the SSL enum cipher scripts. That was just to make it for an easy proof of concept. We're also looking to open source this so that all of you can use it and add to it. We're also looking at additional research to try and make the fingerprints as unique as possible. So they're already looking very promising, but if we can make more unique fingerprints, that's always better. So one of the things we're potentially looking at are like DTLS responses, for instance, or adding more TLS extensions in it. And then finally, we need to version this, because as new TLS extensions and TLS versions come about, the drone fingerprints are going to change. And so that we can share it and keep it reliable, we need to version this.
Yeah, so essentially, we need to do more research and testing, and we also need to rewrite the code to be more performant. And we still have some work to do before we're ready to open source it. But our plan is to open source it and allow anyone to utilize this method to scan whatever they want to scan. And so hopefully, we could end up using services that are using this method to be able to provide us with intel or data that we can use to increase our detection fidelity or compliance checks or whatever.
And with that, thank you. Since we have a little bit of time, we can try and do a live demo real quick, which we'll see how that works, because live demos always go smoothly.
No, it's on your screen.
Yeah, I'll drag it over.
I think we set that to full screen.
Did we?
Yeah.
Oh, that's what it is. Hang on. Just get rid of that. There we go. Okay. So the last time I tried this on our Wi-Fi, it's pretty slow. Let's try that again. Can I zoom in?
Yeah.
Let's try this. How is that? Well, this is the result that I was sharing in the screenshot. Do you know how to zoom in on this?
Command-Shift plus. Yay, man.
Much better. So that took 6 seconds. It's usually less than 1 second, but with the Wi-Fi here and everything, hopefully that's a acceptable result.
But yeah, so it sends a bunch of client hello packets, different client hello packets, in a bunch of different orders to the server, and then it looks at it the way that the server responds to all of those different ones, then concatenates together. You can just kind of draw some similarities to JA3. Then concatenates the output together, and then just MD5 hashes it so that we have a 32-character fingerprint to work with. And before you're like, ooh, MD5, it's like the type of data that we're working with, the amount of data that we're working with, there's like no chance of a hash collision, accidental hash collision or anything like that. So it just makes for an easily consumable, easily shareable 32-character fingerprint. You can tweet the fingerprint and have room to put context around it. That's the if you can't tweet the fingerprint, then it's too long. So that's why we did MD5. Any questions?
Yeah.
So I hear you on MD5. I was just curious if you have looked at all into like defining a vector space and doing any sort of fuzzy matching on the fingerprints that you've received, and whether or not that would actually be useful to you for the goals that you're trying to achieve with this project.
Yeah, that would be it's something that we need to look into. The thing is and it's similar to hash and with JA3 and the way that we've done, and we'll be talking about CU tomorrow. Those different methods is that we kind of want to build this out so it is a method, so that other people can write it in whatever language they want, or other people can build this into whatever they want. And not everything supports fuzzy hashing, and so it makes it harder to implement. Now, with this particular thing, because it is a scanning tool, you're right, we could put in fuzzy hashing on whatever language will allow us to do so. So it's something that we need to look into. Like we said, this isn't done yet. We're just showing you preliminary results. If people have ideas or things that they want to scan with it, we could potentially share what we've got so far, so we can continue the research. But yeah, so great idea, though.
Thank you. I appreciate it.
We should do that.
2 questions. How many Trickbot servers resulted in those 4 hashes?
The entire list that's on abuse.ch, I don't know how many are there. I don't know. It was like 100 or something like that.
And the second question is, have you looked at TLS 103?
Yeah, so basically the Alexa top 1 million, the list there that we showed was like Facebook and Google, and they're all TLS 1.3. So this still works there. And we showed with, if you look up my last talk here from last year on JA3, so like Google, for example, Google Chrome will order its ciphers differently, even though it's using TLS 1.3 versus like Firefox will order its ciphers differently. So even though they're using TLS 1.3 and they have like a smaller cipher set that they'll accept and everything, they're still doing things very different. And the extensions are vastly different. And so it's the same with the servers on TLS 1.3. The extensions, the order in which they use them, that they send back, the ciphers that they accept and all that, still, even with TLS 1.3, still easily fingerprintable, and as we showed with the Alexa Top 1 Million, very unique.
So part of this is because servers need to be maintained for backwards compatibility, they won't just support 1.3 in most cases, so they'll go back to like 1.0 and then support like 1.1, 1.2. But when we go to fingerprint a 1.3 server and we send, say, a 1.2 request, right, it actually sends back in the string a downgrade. So that is actually, I believe, part of our fingerprinting process right now. So at least we know if it supports 1.3. In terms of development, 1.3 is a little bit harder to develop for at the current time because it's a significantly different handshake process.
Thanks, RJ. I forgot about how we were doing different. We were sending 1.2 and 1.3. Any other questions? Yep.
Well, first of all, like really good research. I mean, we use J3 and J3S all the time, so I think this is going to be another, very cool tool to use.
Awesome. Thanks.
So a few observations from some stuff that we have also done in the past. Like, for instance, we combine J3S with data from the response on the HTTP, like the order of the HTTP headers, the hash of the default path, and things like that. So I would recommend that you take a look at combining potentially some of those features. So when you're actively fingerprinting, like, add a default request to the default path and try to gather some of the headers, because we have been pretty successful with that. And actually, we fingerprint Trickbot just with HTTP, the HTTP response. Actually, we haven't done anything from a TLS perspective, but you can probably add more information, especially once you start looking at, besides that 1 million from Alexa, because my understanding is that 1 million is likely biased because companies like Salesforce, Facebook, Google are likely writing their own web servers and things like that, or SSL implementations. But once you go down, everybody's going to be running the same Apache version, blah blah blah. So maybe by combining some of those features in the HTTP headers, you could improve that somehow.
Yeah, that's a great point. Something else that we were also thinking about was, and this would make it easy if it's living, if like Shodan is running this, right? Because then you can cross-reference this JARM hash with the other data that Shodan already has for that server or whatever, to be able to build out even more specific fingerprinting. But yeah, that's a great idea. HTTP fingerprinting is awesome. I wish William Slutsky would let me talk about it, but he won't. I love you, Will.
So the idea of scanning the entire internet has some resource issues. But have you taken a look at it, maybe just like scanning the IP ranges of like some known bulletproof hosters to see if you can find like some C2 servers that are up there that people haven't found yet?
So actually, yeah, good point. So basically, to answer the question of like, most companies can't scan the internet. Their legal department won't let them. But a way that you could use this is to build in some automation. So for every new server that you connect to, you have a host that scans that server that you just saw, the new one that you just saw. And so you're not scanning the internet, you're only scanning things that you're communicating to. And then if something looks suspicious, and you have a list of like bad JARM hashes, then you can cross-reference the JARM hash. And if the JARM hash matches your suspicious list for whatever, increases the suspiciousness of that connection, you can make a decision to kill it. That's one way that we were thinking about deploying this in a way where we're not scanning the internet. So there's lots of possibilities here.
All right. Okay, great. Yeah, that's a great idea.
I think we have time for one more.
All right, thanks, guys.
Thank you.
I was also going to add, this is my first presentation ever.